Hello and welcome to Computer Organization and Architecture class. This video is about the restoring division algorithm. Before starting with the actual topic, I would like to introduce the narrators. We are students of Vishwakarma Institute of Technology, Pune. We are from Group 9 of Division D. These are the names of all the narrators who will be narrating and explaining different parts of this video. Now, let's start with the history and definition of restoring division algorithms. Restoring division algorithm is a method used for division of two binary numbers in computer arithmetic. It is an iterative process that involves comparing the divisor with the dividend and subtracting them until the result is less than 0. Unlike other division algorithms, the restoring division algorithm restores the dividend to its original value after each subtraction, hence the name restoring. The invention of the restoring division algorithm is not attributed to any one person in particular, as it is well-known and widely used algorithm in computer arithmetic. It has been used in various computer systems and architectures since the mid-20th century. However, the first mention of the restoring division algorithm can be traced back to the work of W. W. Peterson and D. E. Weldon, who published a paper in 1957 titled Error Correcting Codes and the Correction of Single, Substitution, Transposition, and Inversion Errors. In this paper, they described the use of the restoring division algorithm for the correction of errors in digital communication systems. Since then, the restoring division algorithm has been widely used in various computer systems, including early IBM mainframe computers, and is still used in some other applications.
Hardware implementation of division restoring algorithm. The restoring division algorithm is a classic technique for performing integer division. It involves redox step that uses arithmetic operation such as addition and subtraction to compute the quotient and remainder of a division operation. The hardware implementation of the restoring division algorithm involves the combination of arithmetic logic unit, registers, and a control logic. Here we have three registers, that is M register, Q register, and A register. In Q register we are storing dividend, and in M register we are storing divisor. The next is a register. We are initially setting A register to 0. A register and M register are of n plus 1 bit. Here, n plus 1 bit of A register is added to n plus 1 bit of M register to get n plus 1 bit adder. The next is a control logic to control actions of left shift addition and subtraction. This will be decided by this control logic. The control logic will send some signals to register for left shift addition and subtraction. The hardware implementation of the Booth's division algorithm can be optimized by using parallel processing techniques and pipelining. Parallel processing involves performing multiple iterations of the algorithm simultaneously using multiple hardware units. Pipelining involves dividing the algorithm into stages and performing multiple bits simultaneously in each stage.
Now let's take a look at the flowchart for the restoring division algorithm and its related terms. First, we initialize the registers where the value of Q is the dividend, M is the divisor, and the value of A is set to 0. The counter N is also set to the number of bits in the dividend. After initializing, the algorithm begins by shifting the contents of registers Q and A towards left as if they were a single unit. This leaves the last bit of Q empty. Then the content of register M is subtracted from A and the result is stored in E. After that, the sign bit of A is checked. If it is 0, the last bit of Q is set to 1. But if it is 1, the last bit of Q is set to 0 and the value of register A is restored to its previous value before subtraction. Then N is decremented. This process is repeated until the value of the counter N becomes 0. After N becomes 0, the algorithm terminates and the register Q contains the quotient while the register A contains the remainder.
Now here we are going to see steps required for division algorithm. Step first. First, the registers are initialized with corresponding values. Here actually what happens when we take the values of dividend, divisor, that values are stored in some register and that register are named as Q, M, A, N. N is the number of bytes which are in dividend. Step second. Then the content of register A and Q is shifted left as if they are a single unit. Here we do shifting in which we shift the bits of A and Q by one position towards left and the least significant bit of Q remains vacant. That vacant position is filled later. We will see in next step. Step 3. The content of register M is subtracted from A and result is stored in A. Here actually we can do addition also, but there we can add A and 2's algorithm of M. Step 4. The most significant bit of A is checked. If it is 0, the least significant bit of Q is set to 1. Otherwise, if it is 1, the least significant bit of Q is set to 0. Now this is which I was talking about. Here we decides that which actually value should be stored in least significant bit of Q. The value of A before the subtraction with M. Step 5. The value of counter N is decremented. Here we decrement the value of N. Step 6. If the value of N becomes 0, we get outside the loop, otherwise we repeat from the step 2. Here what happens, we should repeat the procedure of division algorithm up till the n's value gets 0. Before that we should continue our procedure in loop. Step 7. Finally the register Q contain the quotient and A contain the remainder. Now as I have told that the procedure should be repeated up till the n gets 0. The position where the n gets 0, the corresponding values of Q and A tells us quotient and remainder respectively. Means the value that Q contains is nothing but quotient and A is nothing but remainder.
Now I am going to explain you the restoring division concept by a simple example. Here we are taking 7 divided by 3. 7 is a dividend which is represented by Q and is 111 in binary. Similarly, 3 is divisor represented by M and is 011. As the value of A will be 4 bytes, therefore we set the value of M as 0011 for calculations. The value remains 3. For a part of calculation, instead of actually setting the value of A to A minus M as given in the flowchart, what we do is add A and 2s complement of M, which is shown here by 1s, which is inverting the bits of M, and 2s by adding 1 to 1s complement. The value of 2s complement of M which we get is 1101. Remember this value as we will need it in further calculations. In the given calculation below, where we added 0001 and 1101 which is 2s of M, we get the result 1110. Here the actual meaning remains the same, which is A minus M. Similarly, adding 0011 to 1101, the result we got is 4-bit 0. So this is the table of calculation. Here in the initial step, the value of A is set to 0. The value of Q is 111, which is 7. And this is the initial operation. And the value of N is set to 3, which is the number of bits of Q. So according to the flowchart, what we do next is left shift. So we shift all the digits to the left, and then the least significant bit of Q is set to blank, and the most significant bit is expelled during the calculation. So in the next step, what we do is A is equal to A minus M. This I have previously told you how to do it. A plus 2s complement of M, which is 1101. This is the same calculation which we have done previously. 0001 plus 1101. The result is 1110. So as the most significant bit of A is 1, then what we do is set the value of Q0 to 0 and then restore A. So A is restored. And in the next step, the value of N is decremented, so N becomes 2. Similarly, as N is not equal to 0, so we do is left shift, LSB is blank, MSB is expelled, then A is equal to A minus M. The result is 4 zeros. So as the most significant bit of A is 0, so the Q0 is set to 1. Here in this step we do not restore A, we just take the value of A as it is, and n is decremented, so n becomes 1. Similarly, in the next step what we do is shifting, then entire thing is shifted, and then calculation, and then the MSB is 1. So what we do is set Q0 to 0 and then restore A, so A becomes 0001, and then we decrement n. As we decremented n becomes 0, so we stop here. So in this last step the value of A is 0001. This, which we convert to decimal, becomes 1, and this is the remainder of our calculation. Similarly, Q becomes 010, which we convert to decimal, becomes 2, which is the question. So this is the final result of our entire calculation, which is A is equal to 1 and Q is equal to 2. Here are few examples which you can try yourself. You can do the same steps as we did previously.
Advantages of restoring division algorithm as follows. First, it is relatively simple to understand, implement compared to other division algorithms. Second, it is fast and effective for dividing large numbers, as it typically requires few iterations than other division algorithms. Third, it can be used for both signed and unsigned division, make it versatile algorithm. Fourth, it is easy to modify for use different regex values, example decimal and binary. Fifth, it produces the question and remainder as separate output, which can be useful in current applications.
Now moving forward to the last part of this video, disadvantages of the restoring division algorithm. The restoring division algorithm generally requires more clock cycles to complete than other division algorithms, therefore resulting in longer execution time. The restoring division algorithm is more complex than other division algorithms, making it harder to implement in hardware as well as software. The restoring division algorithm is not particularly efficient when the divisor is too small. One more major disadvantage is limited range. This algorithm is only suitable for performing integer division on positive numbers. It cannot be used to perform division on negative numbers or numbers with fractional parts. Overall, while the restoring division algorithm has some advantages, its disadvantages make it less well suited for certain applications and contexts. That's all from our side. Comment your doubts, we would love to answer them for you. Thanks for watching this video. We hope you would have liked it. If you did, please like the video and share it with your friends. And don't forget to subscribe to this channel. Thank you.